Okay, so big thanks to, I think it was Yash for being the person who solved this problem. And in future, please to the organisers, can we check things like this at the beginning rather than doing it after the start? So I need to then go backwards to show you the things we've missed. So that was the slide I initially was intending to start with, laying out where we were and how to go about asking questions. This was then what you should have been seeing when I was talking about spherical collapse. We've got the parametric solutions. Everything I had carefully practiced is now not working. So can you now see a spherical collapse slide with a laser pointer on it? Yeah, good, thanks. So these are the parametric solutions I was talking about, which apply to a closed universe, but also to our spherical overdensity. And so the point we got to when somebody pointed out the issue was the final expression for how overdense a single dark matter halo is. And the key quantity is this thing, delta, the virial overdensity, which is telling us how overdense the single dark matter halo is relative to the background. And so in the simple top hat model, it turns out you can do an analytic calculation, and the answer you get is 18 pi squared, which is equal to 178, which usually gets approximated to 200. A brief caveat here, which I'll come back to in section 3, is that actually that simple calculation assumes the universe is both flat and completely matter dominated. Whereas we'll see later on today, we think we live in a universe which is made of a mixture of matter and a cosmological constant lambda. So in reality, the number is theoretically slightly different in that case, but that's a small caveat, which we'll come back to later. So that wraps up everything I have to say about structure formation. Is there any questions anyone would like to ask about structure formation at this point?
You said that these parametric solutions also apply to the closed universe. Could you explain that a little bit more, please?
Right, okay, so I don't want to go off on too much of a tangent here, but I'll try to briefly explain this. And actually, the closed universe is their main application. So if we went right the way back to the Friedmann equation that I showed you at the beginning, we sort of looked at the solutions for simple universes that are flat and made of just matter or radiation. And there you've got a simple power law solution that the scale factor A evolves as a power law of time t. However, if you go beyond a universe which is flat and made of just one thing, you end up with two terms on the right-hand side of the Friedmann equation. And you can't come up with a simple solution of just A as a function of time t. Instead, you have these so-called parametric solutions in terms of a parametric variable, which for a closed universe is usually called theta, and the solutions have sine and cos in them. Whereas for an open universe, the variable is usually called psi, and you have parametric solutions with sine and cos in them. And so the net result is that sort of a closed universe starts from 0, scale factor expands out to a maximum, and then gravity, there's enough matter that gravity overcomes the expansion and it recollapses again. Does that help there?
Yes, thank you.
And there was a question in the chat window, is this in the linear overdensity regime? This is all linear analysis, but what I've been saying about spherical collapse is then trying to handle the non-linearities of what happens once a perturbation becomes non-linear, gets greater than 1, and then collapses. So any other questions at this point? Okay, well, in that case, we'll move on to gravitational lensing. And so this is going to be a very rough qualitative overview to just give you a sort of handle of sort of on the main things that are important. And so this figure that you can hopefully see now is a very simple one, lensing by a point source. they've made it a black hole. So you've got an observer on the Earth. In this case, the simple case, they've got a star that's being lensed, and it sits on a source plane, and our lens sits in a lens plane. And without the lens bending space, light would travel on a straight line from the star, but instead, light was initially on this solid line, gets deflected by some angle alpha so that it ends up being seen by the observer. And there are sort of different observational sort of regimes according to how big alpha is. So we'll start off with strong lensing. And if you want or need to learn more about this, I've sort of cited a review there, which is about a decade old. So observational results have changed since then, but theory in this case hasn't. So strong lensing is where that deflection angle alpha is large. So in general, that means you get multiple images of a single source because of the light being bent. A particular case, though, is when you get the source, lens, and observer accidentally perfectly aligned. And in that case, you get a symmetric situation where instead of having multiple images, you get a single Einstein ring. They're very pretty, but they're not that sort of common. They're not the default for what happens. And the reason that I'm mentioning this, strong lensing, is that the properties of the images, i.e. their numbers, their positions, their intensities, depend on the overall mass distribution that's doing the lensing. So typically it won't be a point mass. It'll be, say, a galaxy cluster, which has got galaxies within it. So we'll see later on today, hopefully, that lensing gives us evidence for dark matter. It also turns out, and we'll see this later in the week, that it's very useful for probing the properties of dark matter, i.e. its particle nature, because it allows us to probe what's called substructures, subhalos within larger dark matter halos. And we'll see later on how that can be done. A particular case of strong lensing is what's called microlensing. And so this occurs when the separation of the images is of order micro arc seconds. And so that's just too small for any telescope to be able to see two separate sources. Instead, what you see is a single source, which then, just you see the star or whatever it is you're looking at, and its amplitude constant, and then goes up into a peak, one that gets microlensed by a compact object passing the line of sight between us and the star. And in particular, looking for stars in the small and large Magellanic clouds that are part of the Milky Way, looking for them being microlensed is a really powerful method of looking for compact objects sitting in the halo of the Milky Way. And so this is something that I expect that Bernard Carr and Florian Kuhner will talk about in great detail later in the school, because it's a really useful way of trying to detect dark matter in the form of primordial black holes made in the early universe. The final form of lensing I want to briefly mention is what's called weak lensing. So in this case, the deflection of light, the angle alpha, is really sort of small, too small to sort of measure. So you're not sort of seeing these clear effects, but you're seeing net statistical effects of the distribution of matter that light has passed through on its way to us. And a particular thing is useful is something called cosmic shear. And this is a distortion of the shapes of distant galaxies due to weak lensing as the light passes through matter to us. So this sort of picture here tries to show this. We've got the observer on the left. We've got the galaxies on the right. The green circles are supposed to be their actual sort of shapes of how the images would look like. But in between us and the galaxies, we've got this distribution of matter, these spherical dark matter halos. And so instead of light traveling on this blue straight line, it gets bent and distorted along the way. Well, its path gets bent. And so the net result is that the shapes of the galaxies get distorted. And so this is something that on an event galaxy by galaxy basis, you can't work out what's happened, but statistically, by looking at how the shapes of the galaxies are distorted, you can probe the intervening matter distribution. So any questions about gravitational lensing?
Go ahead.
So sorry, in microlensing, this deflection angle is even smaller than weak lensing, or I mean, I don't really see the difference between microlensing and weak lensing regarding this angle.
Right, so weak lensing would be even smaller deflection. So microlensing is a small deflection from a strong lensing point of view, but it's still that you get multiple images, but the separation is small. Whereas with weak lensing, you don't get multiple images, but you get distortions of shapes of things you're looking at.
Alpha, let's say.
So any more questions? Nothing
From here.
Chat window, so let's carry on. So next up, we're going to spend 5-10 minutes looking at something called inflation. And inflation isn't directly relevant to dark matter, perhaps, or at least the observational evidence for it, but I'm going to mention it for 2 reasons. So the first of these is we've already talked about structure formation from initially small perturbations. And inflation is, as we'll see in a moment, the process that we think generates those initial small fluctuations. And then the second reason for mentioning inflation is that you will hear about it later in the school in the context of particular dark matter candidates, for instance, again, primordial black holes, as it plays a role in their production. So this is a sort of telling you about it briefly to set the scene now. So as I said, what it is it's a postulated, we don't know for sure whether it happened or not, period of accelerated expansion in the early universe. So in other words, the second derivative of the scale factor A is greater than 0. So the universe isn't just expanding, but that expansion is speeding up. And it was proposed in the 1980s to address some potential problems with the Big Bang. On the whole, the Big Bang works fantastically well as a model for the universe, that everything started off very hot and dense and has been expanding and cooling. We've already seen that the predictions of nucleosynthesis match observations really very well, and it also explains the formation of the cosmic microwave background. I don't know of anybody who can tell you where the cosmic microwave background came from without a Big Bang. However, when you look at things in detail, it turns out you have to sort of set the universe up initially to be sort of just so that it evolves to be like the universe we observe today. So there are these 3 problems. The first of them is the flatness problem. Now, the geometry of the universe, i.e. whether it's flat, open or closed, is something that can't be changed. So if the universe is exactly flat, it stays exactly flat for all times. However, it turns out you can see by looking at the Friedmann equation that governs the expansion of the universe, that if the universe isn't exactly flat, say if the density is just above the critical density at some time, then the density evolves away from the critical density as the universe evolves. So, as we'll see later on today, hopefully, actually, we live in a universe that's pretty close to flat. And if it was exactly flat, that's fine. But if it wasn't exactly flat, there's a question of fine-tuning. To be as close to flat as it is today, it would have had to been fine-tuned to be almost exactly flat at really early times just after the Big Bang. That you could maybe explain away as just saying, well, the universe is exactly flat and that's that. That then leaves you, though, with what's called the horizon problem. So the cosmic microwave background radiation that we met earlier has these tiny fluctuations in its temperature. But on the whole, what's remarkable is the temperature is the same in whatever direction we look. And it turns out that you can calculate the size of a region where light would have been able to interact before decoupling when that radiation was released. And so the size of a region which could have been in causal contact and hence in thermal equilibrium. And the size of such a region today would subtend an angle on the sky of about 1 degree. Whereas in fact, when we look at the sky, the distribution of the CMB is the same in all directions, despite the fact that any regions that are separated by more than 1 degree could never have been in causal contact. So again, it's setting up how could the initial conditions have been so that these different regions know to have the same CMB properties. And then finally, the thing which was why people initially proposed inflation, which is less relevant now, but it was a big thing in the 1980s, that this grand unified theories of particle physics that were popular there involved when symmetry broke, monopoles forming, and those monopoles are matter, so they would rapidly come to dominate the universe. Whereas to have nucleosynthesis happening, as we've already seen, you need the universe at early times to be radiation dominated. So if you've got a particle theory that predicts that either monopoles or some other form of massive relic exist, then it's hard to explain how the hot Big Bang can work as well as it does. So then the question is, how does inflation solve these problems? And it does it in sort of different ways. So in terms of the flatness problem, it turns out that this period of accelerated expansion drives the initial density, so it's so close to the critical density that even though it evolves away from it later, if the universe isn't exactly flat, it stays very close to it. The horizon problem is solved because we can take a small patch of the universe that was initially in causal contact and expand it by a huge amount so that all of the currently observable universe originated from this small initial region. And then finally, if you have troublesome massive particles produced, this rapid acceleration, the simplest model is it's exponential, it would just dilute the monopoles away. So those are the reasons why inflation was first proposed, but it turns out to actually do something else that's really useful, which we'll look at in a second. So to make the acceleration of the universe, the expansion of the universe accelerate, i.e. sort of speed up, it turns out you need it to be dominated by something with negative pressure. And in particle theory, the sort of simplest way of doing this is by something called a scalar field that's evolving slowly along its potential. And the Higgs field is a concrete example of a scalar field, so we know that they exist in reality. And so for inflation to happen, the potential has to be quite flat. The scalar field slowly rolls along its potential. Inflation or accelerated expansion has to come to an end to produce the hot Big Bang. So eventually we want the potential to get steep. The field stops slowly rolling, oscillates around the bottom of the potential and decays in a process known as reheating. And that produces a sort of standard hot Big Bang starting off with radiation domination. So what's neat and was realized soon after inflation was proposed is that quantum fluctuations in the scalar field generate scalar perturbations, which are the density perturbations then, which structure formation then happens from. And the details of the power spectrum of those density perturbations depends on the shape of the potential. But very roughly, they're expected to be close to scale invariant, i.e. close to having the same amplitude on all scales, as is now observed in the cosmic microwave background, as I told you about earlier. So there are actually hundreds of models of inflation, and a large swathe of them aren't now consistent with the best CMB data, but broadly speaking, what's observed in the CMB is consistent with the predictions of inflation. So I think I will skip this slide just so that we don't go too slowly and it's not entirely necessary. So I will pause now for any questions on inflation.
Looks like there are no questions.
Okay, thanks. So then we will move on to the final thing I want to say from the introduction to cosmology point of view, and that's a brief mention of type 1a supernovae and the direct evidence that the universe today is accelerating. So we just talked about inflation as a potential period of acceleration in the early universe. What we're now doing is coming back to the present day. And again, this is something that's not directly relevant to the evidence for dark matter, but the cosmological constant, it affects how density perturbations grow and hence how structure forms. And this type 1a supernovae are kind of a key component of our evidence for the standard cosmological model, i.e. lambda CDM. So for those of you who come from a particle physics background, a type 1a supernovae is essentially what you get where you've got a binary star, so two stars orbiting each other. One of them has gone through its life cycle and ended up as a white dwarf, but the binary companion is sort of bigger and behind it, and the white dwarf is accreting matter from the companion, and it can only do so up to something called the Chandrasekhar mass limit, and that's the biggest mass of a star that can be supported by what's called electron degeneracy pressure. And once you go above that, it basically goes boom and explodes, and those explosions are type 1a supernovae. Now, they are what's called a standard candle, and I'll explain why that's useful on the next slide. But actually, the whole truth of the story is they're not an exactly standard candle. So a standard candle is an object that always has the same brightness. And so if you know how bright something actually is, by looking at how bright it appears to you, you can work out how far away it is. So it turns out that they're actually what's called standardizable candles. They're not standard candles. They don't all have the same brightness, but you can do something to them to turn them into a standard candle. So the figure on the right, the top panel has the absolute brightness as a function of time of various different supernovae in different colors. And so you'll see people detect these when a star suddenly gets really bright, and then they monitor them every day to see how that evolves. And so they evolve to a peak and then decline slowly again. And once you know it's a supernova, you then monitor it really carefully. And so the peak brightnesses are all different, but there's a correlation. The brighter something is, the slower it decays. And so this correlation allows them to be mapped onto a sort of standard light curve and to work out how bright they actually were so that they can be used as standard candles. So this allows them to be used to measure something that's called the luminosity distance. So measuring distances in cosmology is difficult. You just can't unfurl a giant ruler. You have to sort of come up with either standard candles or things called standard rulers, objects that are known to have standard extent. And then the distance that you measure using these things depends on how the universe is expanding, which depends on what it's made of. And so in this case, the luminosity distance is the distance you would calculate from an object based on its luminosity and flux, assuming the inverse square law holds. So just that the flux falls off as 1 over the distance squared. In reality, though, this isn't the case, and the expansion of the universe has a few effects. And in particular, the flux is reduced by a factor of 1 plus z squared. As we've already talked about, the energy of individual photons is decreased by redshift by a factor of 1 plus z. And then also the rate at which the photons arrive is also decreased by another factor of 1 plus z. And so that overall ends up with a factor of 1 plus z in the distance. That's for a flat universe. If the universe wasn't flat, it gets more complicated. We have to take into account the area the photons spread out over is changed. But fortunately, assuming the universe is flat, at least for these lectures, is a pretty good assumption. So the luminosity distance for a flat universe is equal to the coordinate distance that we met in the Robertson-Walker metric earlier today, r, times this factor of 1 plus z. And we saw earlier that dr for photons is dt divided by the scale factor. So you take that and integrate it from when the light is emitted up to the present day. Time isn't something we can directly measure. What we can directly measure is redshift. So if you change from time to redshift, you get this expression here. The next couple of steps are some details, but some details I think are useful because they show you why this ends up probing the cosmological parameters in the way it does. And for small redshifts, you can Taylor expand the expression for H as a function of redshift that I showed you earlier for the different components of the universe, radiation, matter, cosmological constant. And you get this expression here. And this thing here called Q is the deceleration parameter. So it's defined as follows here. So it's minus a double dot, so the second time derivative of the scale factor divided by the scale factor times 1 over the Hubble parameter squared. And the minus sign is in here because when people first came up with this, the expectation was the universe was just made of matter, so gravity should be slowing things down. So we would expect it to be decelerating, we'd expect a double dot to be negative, and so then combined with this minus sign, the expectation is you'd then end up with Q being positive. However, as we're going to see in a moment, the actual observational evidence that emerged in the late 90s is that, in fact, in the relatively recent past, the expansion started accelerating. And for a universe made of matter and a cosmological constant, it turns out, using the Friedmann equation, that you can write this expression down the bottom for how the deceleration parameter today, Q0, depends on the matter and cosmological constant densities today. And so this is why luminosity distance as probed by supernova ends up being a good way of probing omega lambda, the cosmological constant density parameter. So the actual results, this is the important bit. So the initial observations indicating accelerated expansion date back to the late 90s. People have now observed of order 1,000 type 1a supernovae. And on the left, we have the results of those observations. So this is essentially the Hubble diagram, the expansion rate of the universe as a function of distance or equivalently redshift Z. So ignore the bottom panel for the moment. So the top is essentially just the luminosity distance, i.e. how far away these things are. And so the different colors here are just different sort of observational campaigns to detect and measure supernovae. And the bottom panel then is the residuals, i.e. take the best fit model and see how the actual data deviates from it. And individual supernovae, the individual data points can differ a fair bit. They've got large error bars, but the point being that you've got 1,000 of them. So once you average them, you really see that you've got this really good fit to the data. So the basic result is that the distant supernovae out at sort of redshift of order 1, they're dimmer than we would have expected them to be if the universe was just made of matter and hence the expansion was slowing down. And so to understand why they're dimmer, the sort of simplest explanation, other than doing really wacky stuff with the properties of supernovae or the properties of dust, is that actually the expansion of the universe is accelerating due to a non-zero cosmological constant. And that's what the plot on the right shows. It shows the constraints on the x-axis on omega matter and on the y-axis on omega lambda, the cosmological constant density parameter. The results from just these supernovae as they are today, the grey region is just the results with statistical errors, and the red region is the results with systematic errors. And so I just want to really labour a point here that we are in a regime of precision cosmology where people can make really precise measurements of cosmological observables. However, we are at the point now where systematic errors, i.e. from uncertainties in the modelling, are comparable to and often larger than the statistical errors. And so that's something to just really bear in mind when sort of looking at observational results and comparing them. So the red and grey blobs are where we currently are, just using supernovae. The black lines are the original results from way back in 1998. So those results, what we see now is consistent, and it's just that the error bars have shrunk with better data. We will see later on that by combining different data sets, i.e. supernovae, cosmic microwave background, large-scale structure, you end up with even better constraints on these parameters. But for reference, for now at least, the flat universe is where omega matter and omega lambda add up to 1, is this dashed line in red, And then the dashed line in blue is just showing you the different regimes of parameter space. Above that line, the universe is accelerating, and below it, it will be decelerating. And so I think at this point, I can answer one of the questions that was asked earlier. And so it's about what is the physics that's driving this accelerated expansion? Is it a simple cosmological constant lambda with equation of state W equals -1, or is it something more complicated? And at the moment, the data is consistent with it just being a cosmological constant. When people combine these results with other measurements, what you end up for the equation of state parameter of the dark energy that's driving the accelerated expansion, you end up with something that's very close to -1, and the deviation is sort of small compared to the error bars. So for now, at least, whatever dark energy is, it looks an awful lot like a cosmological constant. So yeah, I've got a couple more things to wrap up the introduction to cosmology, but let's pause here in case there are any questions specifically about type 1a supernovae and the acceleration of the universe.
You said a second ago that dark energy is looking a lot like a cosmological constant. I don't think I quite understand that. Can you expand on that?
Right, so this comes from the result that's sort of written on this slide here. So the figures I've shown you are assuming it's a cosmological constant, and then what then is the value of its density parameter. People can also do more sophisticated analyses where you vary the density today in dark energy and also drop the assumption that it's a cosmological constant, i.e. that its pressure is equal to minus its energy density. Instead, you allow it to vary, that P equals W times the energy density. And when they do that, what they find is that the equation of state W is, today at least, is -1.01 plus or minus 0.09. So -1 is what you expect for a cosmological constant. Dark energy is anything with equation of state less than -1/3. So it's not ruled out that W isn't exactly equal to -1, but at the moment, the measurements are closing in on -1. No measurement ever proves that a quantity is exactly equal to an integer, but at the moment, as with the data telling us that the geometry of the universe is very close to flat, the data are telling us that dark energy is very close to a cosmological constant in terms of its equation of state.
And just to follow up, can the equation of state vary with time?
Yes, indeed it can. So then, so 0th order cosmological constant, W equals -1. The next thing you can do is W is not -1, but it's constant. But in fact, that's actually not that attractive a theoretical possibility. So I mentioned already that inflation, the models there are driven by slowly rolling scalar fields. And so you might imagine that the same sort of physics would be responsible for the acceleration of the universe today. So it's, you know, a scalar field evolving along its potential. And in those models, you would expect W to vary with time. So what you can do is you can either pick your favorite model, individually constrain it, or people look at constraining parameterizations of the equation of state, either a functional form or principal component analysis, or saying that W has this value for this range of redshifts, this value for another, and so on. So the short answer is yes, W could vary with redshift, and people do look at probing that. So I guess another thing that then sort of is worth making as a general point, the more free parameters your model has, the bigger the errors on those parameters get. So what you really want to do is fit your model with the smallest number of parameters you need to do so well. And more, you know, obviously you go and investigate whether more complex, baroque, better theoretically motivated models are consistent with the data. But you've just got to be careful that with enough free parameters, you can fit anything. So sorry, I went off on a bit of a tangent there, but I think it's an important one.
I think we're okay, right?
Thank you.
Okay, so I will just sort of say a few things to sort of wrap up this first introduction to cosmology section. So we've now got a timeline for the sort of history of the universe. I'm not going right the way back through the QCD phase transition to the electroweak phase transition back to possibly inflation. I'm starting only at about 1 second, and that's the point at which nucleosynthesis, when the nuclei of the light elements have formed. The universe remains radiation dominated up to about 0.05 megayears after the Big Bang. It then transitions to being matter dominated. And at the start of the matter, well, fairly close to the start of the matter dominated regime, we've got sort of a bunch of interesting things happen. We have recombination, which is the nuclei and the electrons coming together to form neutral atoms. Prior to this, the universe has been a thick, gloopy soup you can't see through, but once the universe is neutral, the photons decouple from the baryons and they just free stream through the universe, and those photons are the CMB, which, as we'll see hopefully later today, is a really powerful way of probing what the universe is made of. And we haven't really gone into detail about this, but just to give you a sort of hand-wavy idea of things, structure formation starts about 0.1 gigayears after the Big Bang. So this will be when the first sort of small dark matter halos start to form, and then bigger things form via their merger and accretion. And we'll look more at that tomorrow. We've then got a transition from being matter dominated to the cosmological constant lambda also being important, and the expansion of the universe starting to accelerate. And then today, that's something that actually the age of the universe we calculate once we know the cosmological parameters, i.e. how much of the universe is matter, how much is cosmological constant, how fast it's expanding. And the result of that is that we're living about 13.7 gigayears after the Big Bang. So, yeah, any questions on that timeline?
I don't see any questions.
Okay, thanks. So I will just switch slides to the next section, and this will bear with me. This might take a few seconds.
And there is a question in the chat.
Okay, well, at the moment, I'm struggling to get screen sharing working, so I'll get screen sharing working and then answer the question. I'm getting an error message. It's telling me that screen sharing is temporarily failing, but hopefully just trying again will fix that. So before we go anywhere, can you see a sort of title slide, Dark Matter in Astrophysics / Cosmology? Oh, I've lost the chat window. Let's get the chat window back up again. Yeah, thank you for the people saying yes. And let us check at this point, can you see the slides of advance? So you now get a slide with galaxies, galaxy clusters on. Yes, hopefully that's yeses to the second
Yes,
question.
and there was a question in the chat. It says,
okay,
what is
so
the
let's go back
estimated
up.
timescale of the inflation end?
Oh, yeah, so it's a good question in terms of getting a handle on things. If I was going to pick a time out of thin air, we'd be talking a tiny fraction of a second, like 10 to the minus 30 or something. In more practical terms, it's better specified in terms of the reheat temperature, as in the temperature you end up at after inflation. And so it sort of has to be high enough so that you have nucleosynthesis and any other sort of standard Big Bang processes happening. But I think the sort of bottom line is it's a tiny fraction of a second, and we don't know exactly because inflation is a theoretical proposition at the moment. It's not something we know happened for sure, and exactly when it would end would be model dependent. Okay, so that's a thank you for that question. Just one more question, does that time correspond to the Planck mass? So it's a bit later than the Planck time. So the point is we can't even begin to pretend that we can understand physics and come up with models back to the Planck time. So the Planck time is the point at which we know that then, if not before then, to do physics, we need a theory of quantum gravity that combines general relativity and quantum mechanics. So inflation, we're playing with a tiny fraction of a second, but not as tiny as the fraction of a second as the Planck time. Any more questions? Okay, well, let's move on from our introduction to cosmology to the observational evidence for dark matter. And as you've probably already realized, it's actually almost impossible to separate dark matter from standard cosmology, as in our standard understanding of the universe is sort of related to knowing how much dark matter is in it. So I've tried to separate those things because I thought it was clearer than having them all mishmashed in together. But actually, it turns out it's really difficult to sort of talk about cosmology without preempting results about dark matter. So some of the things I've mentioned, we're now going to see in a bit more detail where they come from. So you should now be able to see sort of outline for this section. This is going to overspill today into tomorrow morning. So shout if you can't sort of see the slide. We're going to start with individual galaxies. So really going back to very astronomical stuff after inflation in the Planck time, and then we're going to move out in scale through galaxy clusters to the anisotropies in the CMB, and then on to large scale structure. So huge long list of further recommended reading here. The most important things are probably the top and the bottom section here. So there's a classic review paper, Particle Dark Matter, Evidence, Candidates and Constraints by Bertoni, Hoper and Silk. It's a Physics Reports article. Physics Reports is the place for review papers. It goes back to 2004, as you can tell from the archive number there. So a lot of the details about constraints and models have changed, but the observational evidence for dark matter, things have been refined as in parameter values, but there's not been such radical changes there. So that would be a good place to go there. A fairly small textbook, which I'd probably recommend generally, is an Introduction to Particle Dark Matter by Stefano Profumo, who's one of the leading particle dark matter theorists in the world. And I think it's based on lectures that he gave at summer schools where he covers all of particle dark matter. And so if you're interested in an introduction to particle dark matter as a whole, get that book. And chapter 1 is the bit that covers the material I'm going to be talking about in this section. Once more, the particle data group is a good place to go, and in particular there's a section of that on particle dark matter which Stefano Profumo wrote with Laura Baudis. He's one of the leading experimentalists in the world, so that's something that really is aimed at experimentalists as well as theorists. I'll skip down to the bottom for textbooks. For the cosmology, again, Barbara Ryden's one is my default go-to. For things related to galaxies, the Bible of the theory of galaxies is Binney and Tremaine's Galactic Dynamics. There is a new textbook which is being written by Joe Bovey. I haven't had a chance to look at it yet, but he's got an online version of it, so that could be a really easy thing to access if you want to know more about galaxies. And then finally, I'm going to be doing this from a what we know now point of view, but there's some things to be said often for understanding the theoretical history of how we got to where we are now, to learn from lessons and mistakes that people have made. And in that case, there are various things you could look at if that's something you think would be interesting. There's a book by Sanders, which is focused very much at the astronomical evidence for dark matter, galaxies, galaxy clusters. Gianfranco Bertoni and Dan Hooper have again written a review here on the history of dark matter. And then there's what looks to be an absolutely phenomenal book by Jim Peoples. He's a Nobel Prize winner. He's one of the big sort of names in cosmology who was behind an awful lot of the developments in theoretical cosmology. It's a really dense book, and I haven't managed to read very much of it yet, but it's a really useful insight in how we got to where we are. And chapters 6 and 7 are the bits that are relevant to dark matter. So, having said that, let's get started. So we're starting off with individual galaxies. And most of the evidence for dark matter in individual galaxies, but not all, comes from what are called galaxy rotation curves. And so in a spiral galaxy, the stars and gas lie in a disk and moving in circular orbits due to the force of gravity. And so you can use the Doppler shift of the hydrogen 21 centimeter line from the spin flipping to measure the speed of the stars and gas clouds. And then, so by mapping out how the speed varies with radius, you can weigh the galaxy essentially. So let's look at that in a bit more detail. So the key thing here is because the stars are moving relatively slowly, a couple of 100 kilometers a second in the Milky Way, this is all just Newtonian gravity. There's no GR here. And so using Newton's laws of gravity, you can relate the circular acceleration, i.e. the rotation speed divided by radius, to the force. And the force is given by the right-hand side of this first expression. And so one thing that gets brushed under the carpet often here is that this is also using something called Newton's second theorem, because actually we're interested in stars which are embedded in the mass distribution. And it turns out that in that case, the force is as if all of the mass interior to the radius the star is sat at was concentrated at the middle. And that's something that it's not a big deal, but it's something that people often don't mention. So the mass which shows up in here is the mass inside the radius of the particular star or gas cloud that you're interested in. And to calculate that, you take the density as a function of radius. It's something that astronomers refer to as the density profile, and you just integrate spherical shells out to the radius you're interested in. So the bottom line is then that we get this expression for how we expect the rotation speed to vary with radius depending on the mass enclosed within that radius. Now, if you go outside the matter distribution, the density will be 0, and hence the mass enclosed doesn't increase as you go further out. So the mass would be constant, and hence we'd expect the rotation speed to fall off as r to the minus a half. And that's often called a Keplerian fall off because that's exactly how the speeds of the planets in the solar system vary with radius. So what you then do is you go out and measure this using the sort of Doppler shift of spectral lines. It's called a rotation curve, a plot of rotation speed as a function of radius. It's been done for hundreds of galaxies. This is just one particular example, gets chosen an awful lot. So for context, this is a smallish dwarf galaxy, and the stars would be sat in the inner few kiloparsecs in the middle. So based on the disk of stars, once you go out to beyond about 5 kiloparsecs, you would expect to get this r to the minus a half fall off, as we've just seen from the equation. However, when you do the observations, the rare stars and clouds of gas at large radii, they're moving around really, really fast. And in fact, their speeds are roughly constant. And I'll come back to that roughly constant in a moment. So this is what's often referred to as a flat rotation curve, the fact it's roughly constant. So let's go back to the equation and see what that tells us. So if we're finding that the rotation speed is roughly constant, that's telling us that the mass within a given radius has to grow proportional to r. So it's not constant, it keeps growing, that actually the density is non-zero in the outer regions. And in fact, to get this exactly flat rotation curve, you have to have the density profile varying as r to the minus 2. So assuming that Newton's laws of gravity are correct, the visible disks of stars that we can see in spiral galaxies are surrounded by these extended, roughly spherical distributions of dark matter known as a dark matter halo. So that's the sort of popular science version of this. Just a few caveats I want to mention now that I'll come back to in the third section of my lectures. The first is that not all rotation curves are exactly flat. And if you put a paper on the archive saying that they are, your inbox will fill up with observational astronomers telling you, oh no, they're not. And so here's two particular examples chosen from a particular survey of nearby dwarf galaxies. Here's an example of one where it falls gently with radius, and here's an example of one where actually it's still growing. So in general, they're close to flat, and there's definitely evidence for dark matter, but just be careful about not saying they're exactly flat. And then the other thing, which we'll link into when we come on to numerical simulations of how we expect dark matter to be distributed tomorrow, actually, to the flat rotation curve corresponds to a density profile that varies as r to the -2. However, the observations only probe a relatively small range of radii. And we'll see tomorrow that simulated dark matter halos have density profiles that are a bit shallower than this in the inner regions of the halos and a bit steeper in the outer regions, but are consistent with the -2 in the regions probed by the data very roughly. So one final thing to say about galaxies before I pause for questions. So the best evidence, the cleanest evidence for dark matter in galaxies definitely comes from galaxy rotation curves, but historically there was another argument, and it's something called disk stability, and just mainly due to Oestreicher and Peebles. And so basically the problem was that if you tried to do a simulation of what's called a self-gravitating disk, so a disk that's held together just by its own gravity, you get what's called a bar instability. You get a bar forming in the middle, and you produce something which doesn't look like a real spiral galaxy, unless the stars are moving around fairly fast. And one way of solving this and preventing this bar instability happening is to embed your disk in a massive extended spherical halo. This isn't quite the strong evidence for dark matter that rotation curves are, because there are other ways that this problem could have been solved. But nonetheless, dark matter existing is a solution to this problem and explains why the disks in spiral galaxies do appear to be stable. So I'll pause now for questions, and I will try and remember to pause before answering them.
Okay.
How do we know from rotation curves that we should get a spherical halo when the galaxy itself is a flat disk or flat-ish disk?
Okay, so that is a good question, and it's one of those things where it's probably not completely evident from what I've told you so far. So you need to have a symmetric extended matter distribution, and I think it's then the fact that you require this to be stable that tells you that it has to be sort of extended in a sort of roughly spherical way. And it might be useful for me to sort of possibly anticipate something that comes later. And it's the fact that the dark matter doesn't interact with the baryons. So it doesn't have any way of losing angular momentum and hence collapsing into a disk. So if you've got dark matter that doesn't interact, it by default then stays out extended. I don't honestly know off the top of my head if you could cook up some form of dark matter that was consistent with rotation curve observations, but somehow collapsed into some fat disk. And that I don't know off the top of my head.
That makes sense. Thank you.
Okay, so by the sounds of things, there's nothing more. So let's move out in scale from individual galaxies to galaxy clusters. So galaxy clusters are groups of tens, hundreds, or thousands of galaxies that are held together by gravity. And as well as containing galaxies, they contain lots of hot gas that emits X-rays. And they are the largest objects in the universe that are held together by gravity. So there is a sort of hand-wavy argument that we expect them to be representative of the universe as a whole. So say if we measure the fraction of matter in a galaxy cluster that's in the form of baryons, it should be roughly the same as for the universe as a whole. And so here's a picture of the Coma cluster, and you can sort of see these extended blobs. They're all galaxies. So galaxy clusters, there are three broadly different types of observation that tell us different things about dark matter, its existence and its properties. And I'll sort of go through them in turn. This slide looks very messy, but it's messy because this is one of the occasions where we can actually go through the gist of the calculation. So this is the thing that Zwicky famously did back in the 1930s, using the virial theorem and the speeds of galaxies to measure the total mass of the galaxy cluster. So I've already mentioned the virial theorem. It's a relationship between the kinetic energy T and the potential energy V, which holds for a self-gravitating system in equilibrium. So something that's held together by its own gravity and has evolved to reach equilibrium. And so in that case, the 2 times the kinetic energy plus the potential energy is 0. And if you want to know more about this sort of thing, then Binney and Tremaine's Galactic Dynamics textbook is the place to go. So what we need to do now is relate the kinetic energy and the potential energy to things that observers can actually measure. So kinetic energy is the sum of mass times velocity squared for each galaxy labeled with an I. The thing you can actually measure by using the Doppler shift to measure the motions of individual galaxies is the mean square velocity, and that's going to be twice the total kinetic energy divided by the total mass. The potential energy, on the other hand, we need to add up the potentials between each individual pair of galaxies, G times the mass of galaxy I, mass of galaxy J divided by Rij, the separation between them, and then sum up over each potential pair whilst not counting the galaxy interacting with itself and dividing by 2 so we don't double count each pair. So then what is typically roughly done is to define a gravitational radius. And so it's basically to come up with a combination of the sums of the products of the masses divided by the distances and the total sum of the mass, which when then substituted into the previous equation gives you this sort of simple relationship for the potential in terms of the total mass, big G, and this gravitational radius. So equipped with the things we've just done, we can work out using the virial theorem that the total mass of the galaxy cluster is this gravitational radius times the mean square speed divided by big G. So you measure the mean square speed from Doppler shifts, you measure this gravitational radius from the projected positions on the sky of the galaxies. And the result of doing this is you measure what's called the mass to light ratio of the galaxy cluster, i.e. its total mass divided by its total luminosity. A dot with a circle in means the sun. So that's the mass of the sun divided by the luminosity of the sun, this factor MO dot divided by LO dot. And so if we assume, and it's not an awful assumption, that stars are not too different from the sun, and if there was no dark matter, then we'd expect this mass to light ratio to be within a factor of a few of the mass to light ratio of the sun. But it's not. It's 400 times bigger. So basically it's telling us that there's a lot more mass in the galaxy cluster than you would expect based on the light. Or to put it in a more popular science way, if the galaxy cluster was just the galaxies we can see, they're moving too fast to be held together by gravity. They just fly apart into space. And so there has to be this extra invisible mass that's holding them together. And in terms of more modern quantities, for instance, the density parameter of matter today, so the fraction of the critical density that's in the form of matter, this is roughly equivalent to that parameter being 0.3. So as I've already mentioned, galaxy clusters don't just contain galaxies, they contain lots of gas that's emitting X-rays. That doesn't solve the problem. The gas can't hold the galaxies together. The gas would also fly off into space. You know, we still need something else to hold the cluster together. But what the gas can do and what X-ray measurements of it can do is probe the baryon fraction. So the fraction of the galaxy cluster that's in the form of baryons. So here we've got the baryon fraction F subscript B is the total mass in baryons divided by the total mass in all forms of matter. And then with our previously stated assumption that clusters are a fair sample of the universe, that ratio we're assuming is roughly equal to the ratio of the density parameter of baryons to the density parameter of matter. So the fraction of the matter in the universe that's in the form of baryons. So on the left, we've got our optical image of the coma cluster again, and on the right, we've got an X-ray image showing this sort of extended distribution of hot X-ray emitting gas. So the physics in this case is that assume the gas is spherically symmetric, and you assume that it's in what's called hydrostatic equilibrium. So the gravity that's trying to pull things together is balanced exactly by the pressure force of the gas. And so then the first equation on this slide holds. The right-hand side is the gravitational force, where again, m less than r is the mass, total mass within a given radius. And then on the left-hand side, we've got the pressure gradient force, which is 1 over the mass density times the pressure gradient with respect to r. So again, the strategy here is to take this equation and rewrite it in terms of things we can actually measure. So this is done using the ideal gas law, which relates the pressure, density and temperature of the gas. So again, Kb is the Boltzmann constant and mu is the relative mass of the things in the gas. And a few lines of maths, what you end up with is this expression here. It looks more complicated, but it has the advantage of being written in terms of things that can be measured. And so the logarithmic gradient of the temperature with radius can be measured from the X-ray spectra, apparently, and the logarithmic gradient of the density can be measured from the surface brightness across the image of the galaxy and the hot X-ray emitting gas. And so when you do that, what you come up with is an estimate for the baryon fraction of about sort of 14–15%. This is a fairly sort of small error. I must admit, I haven't double checked this. I expect that that's probably a statistical error. And so one thing to bear in mind with anything astronomical is there can be systematic errors too. And in particular, this case, we've assumed the cluster is spherically symmetric. It might not be exactly in hydrostatic equilibrium, i.e. it could still be forming and evolving. And then the other thing, which is way beyond the scope of these lectures, but there are uncertainties in how you sort of measure the mass of a cluster from its temperature. So there are uncertainties here, but nonetheless, what we end up with here is a measurement for the baryon fraction, which is consistent with what we get from other types of observation, nuclear synthesis and large-scale structure. So finally, we can measure the mass distribution within a galaxy cluster using gravitational lensing. And so this is strong lensing. We've got the cluster acting as a lens. So this is a really massive object. It's going to bend space a lot. And then in this image, these ghostly arcs are images of a single galaxy that is sat at a high redshift behind the galaxy cluster. And so by looking at the details of this image, you can map out the matter distribution. And so here we've got a sort of 2D slice through it. The spikes correspond to the galaxies that we can see, but the interesting thing is this mound. That's the dark matter that's surrounding the galaxies, and so holding the cluster together. And you could sort of work out from here exactly how it's distributed radially if you wanted to. So one final thing to tell you about galaxy clusters, and then I think that would be a good place to wrap up for today. So this is going to be a bit fiddly. We discovered yesterday when we did a test that videos embedded in Keynote don't work. So I'm going to have to come out of Keynote and share the video separately, but hopefully that will work. So the bullet cluster is a sort of one of a number of sort of special clusters that are in the process of merging. And it was probably the first one to be discovered, so hence it's the one that gets the attention. So on the left, we've got an optical image. On the right, we've got an X-ray image. And it's probably not necessarily particularly obvious to the naked eye, but we've got an overdensity of galaxies on the left, and then a smaller overdensity of galaxies on the right. And what's going on is this is a cluster and a subcluster that are in the process of merging. The subcluster's gone through the main cluster. At some point, gravity is going to be slowing it down. And I think it's known that it's going to stop, turn around, and they're going to oscillate together eventually and merge. And the reason we know that's happening is largely from looking at the X-ray image. So when the subcluster goes through the main cluster, galaxies are actually fairly empty. So the stars and all, the galaxies just pass straight through each other unaffected. However, the X-ray gas is denser and interacts. And so instead what you get, what's shown in this picture on the right, is a bullet-like shock front as the gas from the smaller subcluster has to force its way through the bigger cluster. So let me now see, and hopefully this won't take too long, if we can manage to come out and instead have a look at a video of that, so you don't have to watch me waving my hands around. You can actually watch a video of it. Okay, so can you now see a sort of picture with two blobs? Yes, great. So I will now set this going, and I can't remember which way around this is color coded, whether it's the pinky purple is the gas or the purple is the gas, but we will see as soon as it starts. So here we go. We've got the small cluster going through the bigger one. Okay, and in this case, it's the bluey color that's the galaxies and the dark matter, and that just passes straight through each other. But the pink color is the gas, and we get the shock front, hence the name, the bullet cluster, from the merger. Okay, so let me then go back to my slides and get the chat window back up again. Okay, so can you now see my slides having advanced to a slide with two sort of pretty pictures with galaxies and things on? Yes, great. So we've got the X-ray measurements of where the hot X-ray emitting gas is, and it's caught up in the middle in the gap between the cluster and the subcluster. We know already that the dominant mass component in the galaxy cluster in terms of baryonic mass is the hot X-ray emitting gas. There's more mass in the hot gas than there is in the galaxies. What we can then do is, using weak lensing, i.e. the distortions in the shapes of background galaxies, we can map out the total mass distribution. So everything, the sum of stars, galaxies, gas, dark matter. And when you do that, what you find is these contours in the image on the left. So what those analysis is showing us is that the mass, the total mass, is actually around the galaxies, whereas the dominant baryonic mass is in the gas that's hooked up in the middle. So this is a sort of a very direct piece of evidence for dark matter, in that it's sort of showing us that not just that it's there, but where it is, and that it's around the galaxies. And as we'll see, actually, sort of hopefully in the fourth section, if we get time to it, the fact that the dark matter appears to be around the galaxies and not hooked up in the middle with the gas actually puts limits on how much dark matter can interact with itself. But that's a story for later in the week. So just, one thing which I'll mention at the end of this section tomorrow morning is that sort of all of this evidence we have for dark matter comes from its gravitational effects. And so to do the analysis, you have to assume that you understand gravity. For galaxy rotation curves, it was just Newton's laws of gravity. But once we get out to cosmological observations, it's general relativity. And this particular observation is something that's a real, in my opinion, big challenge for modified gravity models. So, and I'll say a little bit more about this tomorrow, but in principle, you could say, well, maybe dark matter doesn't exist. Maybe we don't understand gravity. And in fact, the laws of gravity are modified, but the bullet cluster is the big challenge here. And it's because it doesn't just tell us that dark matter exists, it tells us that it looks like dark matter is somewhere different from the dominant baryonic component in these sorts of systems. But I'll say a bit more about that tomorrow. So I think it would be a good idea to leave the CMB temperature anisotropies and what they tell us about dark matter for tomorrow. So at this point, has anyone got any questions about galaxy clusters or indeed anything I've said today?
Yeah.
Is there another evidence like the bullet cluster, like some another cluster of galaxies that we can see so clearly the effect of dark matter?
So, as far as I know off the top of my head, the bullet cluster is the case which is most clear cut, but it's by no means the only one of these merging clusters. There's one, I think, called the musket, and there's another one called the train wreck. And I think the train wreck is actually a bit of a mess. It's not just a single big cluster and a subcluster, it's multiple things merging. So there are various other similar systems. And when it comes to looking at constraints on how dark matter self-interacts, those other systems are also really useful. But the bullet cluster is always the one that's the poster child for merging clusters and dark matter. That's partly because it's such a clean case, but I think it's probably partly also that it was the first one, and hence it grabbed the attention and kept it. So we've got a couple of questions in the chat window if there's nothing in the room.
Yeah, I think we're done here. Oh, one
Okay,
more.
so I'll
So I really don't know much about this, so sorry if I will be vague. But what I read from some, like, in principle, valid physicist on Twitter is that there is some, like, first of all, there's some simulations that essentially show that the evidence from the bullet cluster is like more of a problem for dark matter particle candidates than they are for modified Newtonian gravity. And that will also be because the idea that modified Newtonian gravity, like in modified Newtonian gravity, the center of gravitational pull is like correlated with the visible mass is not entirely true.
So I must admit, I don't 100% understand the last bit of what you said, but I can nonetheless say some things that might hopefully be useful. So the first thing I'm going to say, I was going to save to tomorrow, but I'll say it now instead. As I'm guessing most of you are probably aware already, there is a community of people who work on dark matter, and there's a community of people who work on modified gravity. And a lot of the people involved, but not all by any means, are really very polarized. The people who are proponents of dark matter, and in particular modified gravity, and in particular MOND, are very much dark matter is nonsense, you haven't detected it, it's all wrong, you've built this castle of things and it's just no observational evidence. And the people who work on dark matter are like, no, modifying gravity is ridiculous, blah, 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 blah. Obviously, I'm biased, I work on dark matter, but I think actually, reality lies somewhere in the middle of these extreme positions. And so my view on this is there's this whole diverse range of evidence for dark matter that we're halfway through looking at. And in principle, it's, you know, it's really sensible to think, well, actually, are we sure about this? Is it instead that we don't understand gravity? But it seems really challenging to come up with a model that explains everything. And that, I'm not saying it's impossible, but I'm just saying that I'm not aware of anybody who's done it yet. Now, trying to address your specific question, I must admit I didn't quite understand the last sentence of it. I am aware of there being claims a few years ago that actually the very existence of the bullet cluster, i.e. how fast the subcluster is moving, is incompatible with lambda CDM. I can't remember, I think it was perhaps that it's too extreme, it's moving too fast. But my understanding is that when people went back and looked at this in a bit more detail, looked at the uncertainties on how fast it's moving, looked at the simulations more carefully, that yes, it's a very rare system, but we sort of knew that, and it's not impossible. So those are the claims about the bullet cluster being a problem for lambda CDM that I'm aware of, but it sounds like that's not what you were referring to. So could you possibly sort of elaborate about the last thing you said about center of mass?
Yeah, I mean, as I said, it's not something I know too much about, but essentially, like, the claim was that, like, simplistically speaking, the idea why, like, the bullet cluster would support, like, particle dark matter is also related to the fact that, like, the center of gravitational attraction and the visible mass do not coincide.
So I must admit, I'm not aware of that claim. If you can remember anything more about it, i.e. if you can think about who said it or where it was said, either email me or stick something in the Padlet thing that I put the URL of on my first slide and in the chat, and I will have a look in more detail at that. But I'm afraid that that's a question that off the top of my head, I can't say anything sensible about. So any more questions in the room before I have a go at the ones in the...
email you the Twitter chat.
Okay, thank you. So any more questions in the room before I have a go at the ones in the chat window?
I don't see any. I think we're done.
Okay, well, we've got 3 in the chat window, which I'll try and have a go at, but I've just realized the battery on my iPad's just about to die. Hopefully it will hang on. So the first one, could you elaborate a bit more about the self-gravitating disks being an evidence for dark matter? So what it is, in fact, is that they're not self-gravitating in reality. They actually have dark matter. And so the argument is that if you didn't have spiral galaxies being surrounded by a dark matter halo, what would happen would be that sort of gravity pulls the stars into the middle and forms bars. And I think it's actually a more complicated effect than this. It was something that was seen in numerical simulations rather than analytically. And so it's, maybe I've confused issues by even mentioning this to you. The simple evidence is from galaxy rotation curves, but dark matter halos also sort of help us understand that how spiral galaxies can have these nice spiral arms without huge, big, great, chunky bars in the middle. Second question from the chat window, what does the velocity distribution of galaxies in a galaxy cluster tell us about the distribution of dark matter in a cluster? I'm not sure that the distribution of the velocities tells us anything. Yeah, I'm not quite sure about the question. Maybe if you could elaborate, but the average velocities end up telling us about the total mass, and then the positions of the galaxies, well, not the galaxies themselves, but the lensing images then tell us about the mass distribution. But maybe you've got some specific observation in mind that I'm not aware of. So if that is the case, then stick some more detail either in the chat window or in an email to me. And then the final question we've got, do the n-body simulations that favour a cuspy density profile in galaxies introduce a significant disagreement with observed rotation curves? And this is a really excellent question. And I will say, so part of this, the cuspy density profiles, I'll come on to either tomorrow or on Thursday about what numerical simulations tell us about, well, actually, I'm going to talk about both what numerical simulations and observations tell us about the actual density distributions in galaxies. The short answer to your question right now is it's a sort of maybe, maybe not. And it's one of those issues that at one point, simulators were saying cuspy profiles, observers were saying chord profiles with a constant density, and there looked like there was a discrepancy. My understanding, but we'll come back to this later in the week, is that once you take into account baryonic physics, it's not 100% clear that what the simulations and the observations are seeing is completely consistent, but that there isn't an obvious clear discrepancy. But I think this is an excellent question, and we can probably come back to it in more detail later in the week. So any more questions for now? I know we're now at the point you're probably needing a break. So as I said earlier, any other questions, in particular detailed things or things that go beyond the scope of the lectures, either email me, or there's the URL that I put in the chat window, and I can share it with the organisers if that's helpful, where you can sort of post questions on a web page, and that's probably a good way of sort of asking questions that might be useful to a wider range of people. But otherwise, tomorrow morning, I think I will be finishing off the observational evidence.
Well, one question.
Yeah.
I noticed on the email, we got an email of your notes on the side post. Is there access to your slides somewhere that I missed?
So I can give them to the organisers, or I can upload them to Indico, whichever people want. But yeah, we should make sure they're available somehow. I will liaise with the organisers afterwards to make sure that happens. So I think
There's one more question in the chat, it seems.
Okay, so why the bullet cluster stimulation doesn't show the effects of gravitational tides on dark matter. What do you mean by gravitational tides here? Do you mean tidal stripping? Because if you mean tidal stripping, that's something we'll come on to in section 3, either tomorrow or on Thursday. Okay, I'm keeping an eye on the chat window and I can't see a sort of, so I guess the final thing I was going to say, so the plan for tomorrow is we finish off the observational evidence for dark matter from the CMB and large scale structure, and then we start looking at the distribution of dark matter, both what numerical simulations and observations tell us about that. And by distribution, I mean distribution within individual galaxies, in particular the Milky Way. But yeah, that's it from me, unless there are any more questions.
No, I think we're done. Thank you, Anne.
Thank you.